Discrete random variable. This topic would address the course outcome. Compute the probability distribution of a random variable for both discrete and continuous data. The intended learning outcomes are to determine the probabilities from probability mass function and the reverse. Determine the probabilities from cumulative distribution function and cumulative distribution functions from the probability mass functions and the reverse. Calculate the means and variances from the discrete random variables. Understand the assumptions for some continuous, for some common discrete probability distributions, and select an appropriate discrete probability distribution to calculate probabilities in specific applications. And calculate the probabilities, determine means and variances for some common discrete probability distributions. Random variables. A random variable is a function that assigns a real number to each outcome in the sample space of a random experiment. For our notation, we use uppercase letters such as capital X to denote the random variable, and the lowercase would be the elements of the random variable. So let the random variable X be the measured value of current. So the measured value is denoted by a lowercase such as X equal to 70 milliamperes. For multiple values, subscripts can be used. Our random variables can be discrete or continuous. It is discrete if it has a finite or countable infinite range, while it is continuous when it is based on a specific interval. These are some of the examples. For the discrete, number of scratches, number of transmitted bits in error. For continuous, we have current, length, pressure, temperature, time, volume, voltage, and weight. Let us answer the following items. Decide whether discrete or continuous random variable is the best model for each of the following variables. A. The time until projectile returns to Earth. So here, the quantity is time, and time is continuous. The number of times a transistor in a computer memory changes state in one operation. So this is number of times. Number of times is discrete. It can be 1 time, 2 times, 5 times, 100 times. The volume of gasoline. The volume of gasoline that is lost to evaporation during the filling of a gas tank is a continuous random variable. It is a measured quantity. The outside diameter of a machine shaft. So this is diameter and this is continuous. The number of cracks. So it can be 1 crack, 2 cracks. So this is discrete. Same concept. Weight of an injection molded part. So the weight is a measured quantity. So it is continuous. Number of molecules. So this is discrete. Concentration. Concentration is also a continuous quantity. Current. As a previous example, this is also a continuous random variable. If for every event in the random variable there exists a certain probability, we will be having the probability mass function. So let us have our abbreviation for this one, PMF, probability mass function. For a discrete random variable x with a possible values x1, x2, x3 up to x sub n, a probability mass function is a function such that f of x is greater than or equal to 0. So it should always be positive. Summation of f of x is equal to 1. So total area or total must always be 1. So there would be no probabilities greater than 1 because the total is only positive 1. And to get the probability of a certain event, f of x, or the probability that the random variable x takes the value of x, it would just be f of x, or we plug in the value xi to the probability mass function f of x. For cumulative distribution function, we are going to designate this as capital F of x. The cumulative distribution function of a discrete random variable capital X, denoted by f of x, is given by f of x equal to the probability of x less than or equal to x, which is the summation of f of x for all values less than x. So for the discrete random variable x, it satisfies the following properties. F of x is the probability of the random variable x taking values less than x is equal to the summation of f of x for all values of x less than x. The cumulative distribution function takes values in between 0 and 1, and if x is less than y, then f of x must be less than or equal to f of y. For the mathematical expectation or the expected value of the random variable, if x is a discrete random variable with a probability mass function f of x, the expected value of h of x is the summation of the product of h of x and its corresponding f of x. While the mean of the random variable, the mean of or the expected value of the discrete random variable x is denoted by mu, which is expected value of x, is equal to the summation of x times f of x. While the variance of x denoted by v of x is equal to sigma squared equal to v of x, which is the expected value of x minus mu squared, which is also equal to the summation of x minus mu squared f of x, or the summation of x squared f of x minus mu squared. So we can have a simplification about that. While the standard deviation of x is given by sigma equal to square root of sigma squared. We can have some law of expectation. For the laws of mathematical expectation, one, the expected value of a constant is the constant. So the expected value of 5 is 5. Next, the expected value of x is the mean. Third, we can also have the expected value of ax. A can be factored out, so that is a times the expected value of x. So if each of the variable is multiplied by a constant, so the mean is also multiplied by that same constant. So therefore, if we want to have the expected value of ax plus b, it would be a expected value of x plus b. So the expected value of ax plus the expected value of b. And the expected value of ax is a expected value of x plus b. For variances, the variance of ax is equal to a squared variance of x, and the variance of a constant is 0, while the variance of ax plus b is equal to a squared times the variance of x. Let's have some examples. The sample space of a random experiment is A, B, C, D, E, and F. So the possible outcomes are only A, B, C, D, E, and F. And each outcome is equally likely. So there are equal chances. Determine the probability mass function of X. Use the probability mass function to determine the following probabilities. Now take note that the probability for A is 0, the probability for B is also 0, C is 1.5, D is 1.5, E is 2, and F is 3. But take note that the random variable X takes only the possible values 0, 1.5, 2, and 3. So its corresponding PMF, or probability mass function f of x, is equal to, so there are 1, 2, 3, 4, 5, 6 possible outcomes. So that would be 1 over 6, 1 over 6, 1 over 6, 1 over 6, and so on. So there are two 1 over 6s here. So this means we have 2 over 6. So for 1.5, we also have 2 over 6, and then 1 over 6, 1 over 6. So this is the probability mass function of the given distribution, or the given random variable x. Use the probability mass function to evaluate the following. Letter A. What is the probability that x is equal to 1.5? The probability that x is equal to 1.5 is f of 1.5, and that is correct, 2 over 6. So you can simplify that as 1 over 3. Letter B. What is the probability that x takes values from 0.5 or 1/2 to 2.7? What is the value of x that falls between 0.5 and 2.7? So that would be f of 1.5 plus f of 2. So that would be 2 over 6 plus 1 over 6, and that is 1/2. Letter C. What is the probability that x is greater than 3? So there's no value greater than 3, so that is f of an empty set. So that is 0. There is no value of x greater than 3. D. What is the probability that x is greater than or equal to 0 but less than 2? So it would be 0 and 1.5. So f of 0 and f of 1.5. So f of 0 is 2 over 6, and f of 1.5 is also 2 over 6. So this would be 4 over 6. Next, letter E. For letter E, we're looking for the probability that x is equal to 0 or x is equal to 2. So it would be f of 0 or f of 2. F of 0 is 2 over 6 plus 1 over 6, so this is 1/2. Next, determine the cumulative distribution function of the random variable in exercise 3-16. So from this problem, let us solve the cumulative distribution function. As a hint, you should always start with 0 and end with 1. This is when x is less than the lowest variable, 0, and it is 1 when x is greater than or equal to 3. So 0 when it is less than the lowest variable, lowest random variable, and it is 1 when it is equal to the highest. So we start with 2 over 6. So that would be when x is greater than or equal to 0. 2 over 6 plus 2 over 6 is 4 over 6. When x is greater than or equal to 1.5. 4 over 6 plus 1 over 6 is 5 over 6 when x is greater than or equal to 2. And it is 5 over 6 plus 1 over 6 is 6 over 6 when x is greater than or equal to 3. So this is less than 1.5, less than 2, less than 3. So this is our cumulative distribution function of the random variable. Now let's have mean and variance. For the mean and variance, the mean is the expected value of x, which is equal to the summation of x times f of x. So that means for every value of x, 0 plus 1.5 plus 2 plus 3, we are going to multiply their probability. 2 over 6, 2 over 6, 1 over 6, 1 over 6. So the mean is, so to calculate that, so what's the result? So this is 4 over 3. For variance, we have the formula expected value of x squared minus mean squared. So that would be, so the variance is 0 squared times 2 over 6 plus 1.5 squared times 2 over 6 plus 2 squared times 1 over 6 plus 3 squared times 1 over 6 minus 4 over 3 squared. So we can compute for the variance to be equal to please verify if you get the same answer, 41 over 36. Okay, so if we want to get the standard deviation, it would be the square root of 41 over 36. It should be 36. And these are used for this discussion.